Hi everyone, this is Jianting Zhang from Purdue University. So today I'm going to give a short talk for presenting our project. And this is a course project uh, of the CS536, the Data Communication and Computer Networks, which is taught by Professor Chen Yipeng. And below is the course website, from which you could find all the materials you wanted. Okay, let's start it. The title of this project is Availability Priority State Synchronization for Blockchain Sharding System. So first, let's talk about the blockchain sharding. So I think most of you have heard the concept of blockchain. Even though blockchain has been developed for near 50 years, the major challenge of the blockchain is how to scale the blockchain, that's how to improve the performance of blockchain. So sharding technology is one of the promising solutions to scale the blockchain. The idea of sharding is to divide the system into multiple smaller groups, by which each group, or we call the shards, has divided the workload of the whole system. So specifically, in a sharding system, each shard can handle transaction in parallel. So the transaction throughput can be increased significantly. And another feature of the sharding is in the sharding system, then each node only need to store a subset of the data because the whole data has been divided into different groups for maintenance. But the sharding also introduced some new challenges. For example, let's see these figures. The node in the green shard hope to move to the blue shard. So he has to synchronize the whole data of the blue shard before he can be accepted by the blue shard, which means if he hope to verify the transaction in the blue shard, he need to synchronize the data or download the data before he has the capability to verify the new transactions. So this mechanism also called the shard reconfiguration. Actually, the shard reconfiguration is designed to guarantee the security of a sharding system, because in real work, the nodes may suffer from different attack. One of the most famous attack is called the adaptive attack. So in this attack, the shards could be to be bribable, or could be suffer from some DOS attack. So the system has to adjust the shards. For example, the system choose some of the nodes from the green shards to assign them to the blue shards in order to maintain the balance of different shards. So here comes one important thing. So in these procedures, how the system or how the move nodes to synchronize the data, because once they are assigned into another shard, they have to download the whole data of the new shards in order to verify the transaction. However, the existing synchronization protocol asks the move nodes to download the whole data before being accepted by the new shard, which means if the nodes hope to participate in the verification of the new shards, only after he download the whole data can he start doing this. So here comes some questions. So could we decide a mechanism that could help the move nodes efficiently synchronize the data. So in this project, we give a certain answers. But before we talk about it, let's give one observation. So actually, not all the history data are used in the future verification. For example, some data may be out of the date, or some data may be useless and would never be used in the future transaction. So which means we can only synchronize some of the data in order to make the move nodes to be accepted by the new shards. So our target of this protocol is to enable move nodes to be accepted by the new shards as soon as possible. So the main idea is comes from a new concept called availability priority synchronization. The availability here means the move nodes could be accepted by the new shard. So specifically, we first synchronize those data that are accessed recently, because these data may be accessed in the futures if they are they are accessed frequently. So here is the architecture of our project, and actually this architecture consists of 3 layers of the computer network: the application layer, the transport layer, and the network layer. So in the network layers, we use the IPv4 for routing the package, or for communication between the nodes. And in the transport, we use the TCP to show how the package can reach the destination. And in the application layers, we implement 2 protocol. The one is what we just talked about. It's called the state synchronization protocol. Another is a basic application protocol called the consensus protocol, which will be used to help all the nodes in the same shard to maintain the consistent ledger. So next, I will give a demo. So all the codes are public in my GitHub repository. So you could type the synchsize from the GitHub, or just use this link to get the source code. So for illustrations, I use the VS Code to show how our protocol works, and as well as talking about some importance the source codes of these projects. So here are 2 important files. The first is called the application. So in this file, you will find there is an ABCI file. By the way, we implement this project in Go language, because the Go language is very popular in blockchain field. So in the ABCI point code, we actually implement basic consensus procedures. For example, the begin block and the deliver transaction. And in the deliver transaction functions, we will implement how the sharding system executed the transaction, and to count the frequencies of some kits which will be used to compute the latency later. And okay, so another file is called validators. So in this file, we implement blockchain, and blockchain you can consider blockchain as a database. So specifically, you can consider it as a key value database. And there are some parameters of the blockchain. And here are some functions, yeah. And to test our project, we also implement some clients. For example, this is a code to show how our consensus nodes are start. So here you can give some parameters, and these parameters you can find in the GitHub. So there are lots of parameters with different meanings. And we also implement clients and clients. Okay, so because of the limited times, I will directly show how to start our test. So first, you need to run scripts, and these scripts will initialize 2 shards, and each shard will have 2 validators. And then you will run clients that will continuously send transaction to the sharding system. And after that, you could use command or to send some synchronization requests, and this request will be handled by the shard system and will be used to compute the latency and some very useful informations. For example, I ran this command again and again in order to get lots of information. And actually the default running time is 120 seconds, but because of the times, I need to terminate them in advance. And after running this, you in your temporary log, you will find a new file, and this file will contains of the log of these 4 nodes. So for example, when we open one log, we will find that okay, so here's the high, the high, when the block high is 5, the transaction the number of transactions is 100. So let's search. So here we computed the latency of our protocol. For example, when we need to synchronize the block size 13, which means we need to synchronize 13 block, then our protocol needs 5 seconds, while the traditional method needs 13 seconds. And the below is some frequencies of the key, which means how they will be they indicated how frequent the key are accessed during the 13 block. And let's see another. Yeah, so for example, when the block high is 20s, and all this latency will be recomputed. And if you find that with the increasing block high, the latency will increases. Actually, currently the blockchain has a very large storage, and the block height is like thousands of 10,000s of it's very large. So when we synchronize them in that codes, it will require lots of times. So let's give conclusions. Our protocol actually we actually decide our protocol to help the nodes in the sharding system to quickly and efficiently and securely synchronize the blockchain data. So which will be very useful in the sharding system. So that's it. Thank you for your listening.